Welcome back. This is Fundamentals of Micro and Nanofabrication. I am Swayam and today we are going to talk about chemical vapor deposition and some of its basics. This is the ongoing module on additive processing. So, basically what is CVD? As the name suggests, CVD is using chemistry to cause a reaction on top of a substrate to cause a certain material to deposit. So, at a very high level you can look at this figure, and what it shows is that you have a chamber, and chamber is what is enclosing the vapor. You provide some amount of energy to the system, and that energy is typically provided thermally, which is what is being represented here by the heating coils, but in other cases this energy can also be RF power, it can also be radiative energy, etc. The precursor is the chemical that is actually causing the reaction. I will talk more about it in a minute, but typically it is a one or two component chemical that reacts to form the material that you want to deposit. At any given moment in time, you have a certain amount of deposited thickness, and the chemical reaction is happening on top of this deposited layer. This deposited layer, for mechanical and as well as other reasons, requires a substrate. So, this could be any of the wafer, any wafer or any other substrate that we have discussed before, and this whole assembly sits on a susceptor, which is just a mechanical support that holds the wafer while the deposition is going on. There are certain characteristics that this susceptor must fulfill. You can guess that cleanliness is one of them, but there are a few others. So, in very general terms, these are the various components of a typical chemical vapor deposition system. What we will next do is look at a little bit of details of each of them. So, in general, CVD is used to deposit very high quality film. Chemical vapor deposition films have very low contamination, can be often epitaxial or crystalline, often single crystalline, and all of these advantages mean that they are perfect to grow device grade semiconducting material. Epitaxy, if you do not know, refers to when you grow single crystalline material on top of an existing single crystalline material. So, silicon epitaxy on silicon substrate would basically mean that you have a single crystalline silicon and then you are growing another layer of silicon on top, but that layer of silicon is perfectly lattice matched with the underlying silicon. If the orientation is perfect, if there are no grain boundaries, and if the grain boundaries are very large, then you would say that this is an epitaxial growth. Applications are several. They start from high mobility transistors that are commonplace in modern CMOS fabrication. You can also use a CVD to grow heterojunctions. Hetero, as the word suggests, is different. So, silicon germanium on silicon would be considered a heterojunction, or titanium dioxide on silicon may be considered a heterojunction. A great advantage of epitaxial films is that you can start with a native substrate, but then deposit a material that is completely different. A very good example of this is gallium nitride, which is often grown on silicon substrates, sapphire substrates, or sometimes silicon carbide substrates. This is especially useful for materials that are either very hard to grow in a single crystalline form, or are very expensive to grow in a single crystalline form, or if you just want to make a heterostructure where the native substrate is different, but just to enhance the characteristics of the device or to get some new functionality, you deposit a completely new material on top of that native substrate. This is becoming actually increasingly important in the modern world, where heterogeneous integration is becoming important, but that is a topic of a separate lecture. We are also using CVD to grow high quality thin films, not necessarily crystalline or epitaxial, but high quality thin films. A good example of that would be the polysilicon electrode layer that is deposited on top of gate in CMOS. In some cases, even metal films are deposited with CVD, especially if high aspect ratios need to be filled. And then the third and a very important application of CVD is deposition of dielectrics, often on top of metal, sometimes directly on native substrates. Silicon nitride, silicon oxide are commonly grown with CVD and related methods. However, there are advantages or disadvantages to any technique, and CVD is no exception. So, one of the advantages is there is a very wide range of materials. The ability to do CVD is only limited by your ability to provide a suitable precursor, and because chemists are very experienced and good at their jobs, they have figured out ways of converting virtually every element that we know of into a precursor that can be used for CVD. A lot of the silicate based CVD and a lot of the high quality CVD is often done using gaseous precursors. This provides an added advantage that gaseous precursors can be highly purified. Practically speaking, if you were to buy a chemical and it is a liquid, it is hard to get purity better than 3 nines or 4 nines, which is 99.99. But for gaseous precursors, the purities can be much better. They can be 10 to the power, they can be in ppm levels. So, 6 Ns, 7 Ns are available. CVD is a very mature technology. People have been doing CVD for a very long time, even in commercial production as far back as the 1980s, maybe even slightly earlier. And that maturity means that there is a lot of institutional knowledge on how to do it well. I will show you some examples. In CVD, the deposition is strongly dependent on temperature. That is not very surprising because chemical reactions are often strongly dependent on temperature. And which is the Arrhenius, which is also given by the Arrhenius relation, which I think we discussed in a different context a few lectures back. The consequence of strong temperature dependence is that CVD often tends to be conformal. So, the definition of conformality we discussed in the previous lecture, and it basically means that if you have a certain topology, how uniformly are you depositing on top of that topology. And if the reactions are only dependent on temperature and are substrate independent, then it is not too hard to imagine that if you were, as long as you maintain the temperature uniformity, the deposition would also be uniform. It would not necessarily care about the topology underneath and would coat everything uniformly. You can get very high deposition rates, especially if you can figure out how to transport a lot of the precursor onto the substrate. More on this maybe a lecture or two later. And it does not need high vacuum. So, vacuum can come in several grades. Do you want millitorr levels of vacuum? Do you want 10 to the power minus 6 levels of vacuum, or do you want 10 to the power minus 9 levels of vacuum? The more vacuum you need, or the higher grade of vacuum you need, the more expensive the equipment, the more expensive it is to maintain that equipment, and in general lower the throughput, because it takes some amount of time to actually maintain that vacuum, get to that vacuum, and higher the vacuum, the harder it is to get there, or longer it takes to get there. So, CVD is one technique where we are around millitorr, maybe higher than millitorr, torrs or a few torr range. So, that is not a very low pressure, and it can easily be achieved by typical rotary pumps. So, that is an advantage. The disadvantage of CVD is it is costly compared to physical vapor deposition, which we shall tackle in the next module. CVD is definitely much more expensive, partly because, as we shall see, precursors are dangerous. They are expensive chemicals. In order to purify the precursors, a lot of the material gets lost, so they also tend to be very expensive. And running costs tend to be high, because in order to do CVD right, or at least safely and in a repeatable fashion, there is a lot of supporting infrastructure that is required. You need exhausts, you need scrubbers, you need very good gas cabinets, you need gas detectors. The technique is a little complex, so you need very highly skilled workers, and all of this sort of tends to add to the operation cost of a CVD equipment. The other disadvantage is that high quality CVD, especially epitaxial CVD, often requires high temperatures. Now, high is a relative word, but typically for silicon, high quality silicon CVD, you need temperatures in excess of, let us say, 700–800 degrees C. This has certain consequences on cost, which we have discussed, but there are also consequences on stress that develops in the film, because once you deposit a film at those high temperatures and then you cool it down, then it can have some residual stress, which can cause problems. This is especially important if your lattice is mismatched. This is especially important if the film that you are trying to grow on the substrate does not necessarily like to nucleate on the surface very well. We shall look into all these details a little bit later. And of course, high temperature also means that there is a short list of substrates that you can reasonably use. We have discussed the issues of contaminations a lot in previous past. So, steel may not be a very good substrate for CVD, because steel has iron, and iron will diffuse at high temperatures, and if CVD requires those high temperatures, then it will contaminate the film that you are trying to grow. So, your substrates must be non-contaminating, your substrates must be able to withstand the temperature. You cannot do CVD at 700-800 degrees C on a plastic substrate. There is no plastic that will withstand that sort of temperature. Even substrates like glass may not be able to withstand that temperature. So, that reduces your options. And lastly, CVD is often a kinetic or thermodynamically limited, is often thermodynamically limited process, rarely kinetically limited process. And that allows you to only have two parameters to really control the reaction. One is pressure, one is temperature. Other than these two, you don't really have a lever to control the reaction, the way the reaction is occurring, and hence control the properties of the eventual film. The other extreme would be, say, physical vapor deposition, where in sputtering you have access to bias voltages, you have access to temperature, you have access to pressure, you have access to stoichiometry, you have access to different type of targets, etc. So, in that way CVD is a little restrictive. Of course, the flip side of that is it's relatively easy to control and it's repeatable, while some of the PVD processes tend to not be. So, what do we need for CVD? I am just again using the same figure that I used a couple of slides ago, and I'll just want to highlight the various important things that are required, right. So, we need a precursor, a compound that participates in the chemical reaction and produces the compound of interest, the one that we want to deposit. Then we need a substrate which can withstand the high temperature. We need a chamber, and that again needs to be inert, non-contaminating. In general, quartz or steel chambers suffice. Steel in those cases where the chamber does not heat up, and quartz in those cases where the chamber does heat up. We need a susceptor to hold the substrate. It must also be inert and non-contaminating. It needs to withstand the deposition temperatures, because it is always going to be at almost the same temperature as the wafer. Often this is graphite, quartz, silicon carbide. In cases where the temperature is relatively low, say in atomic layer deposition, as we shall discuss later, it can be steel, but not for ultra high or ultra pure or ultra high temperature applications. And finally, we need a heater. This can just be a nichrome wire, which is a thermal contact heating method. It can be infrared radiation, which heats in a non-contact fashion. It can also be RF induction heater, very similar to an induction cook oven that you may have in your home. So, let us talk about precursor first. So, an ideal precursor is one that is volatile, because chemical vapor deposition is done best in the wafer form. While there are, they have in the recent past some techniques that have been developed for liquid precursors, say mist CVD or nozzle based CVDs that actually use liquid precursors. By and large, traditional CVD has always used gaseous precursors. Now, for cases where the precursors are liquid, you can still use them by just vaporizing the liquid into a vapor form and then using those vapors. But still, you need a volatile precursor that you can actually convert to vapors. This precursor must also be hence liquid/gas at room temperature. Solid phase is usually not preferred, though in some cases you can get solids that will sublime at a slightly higher temperature and hence can be used as precursors. Solids, however, even in those cases are a little hard to purify and are often not used. It must be thermally stable. You want your precursor to do the chemical reaction you want only inside the chamber, not in the tank where it is stored, not in the gas lines where it is being transported, and not in the pump where the byproducts will go. It should decompose cleanly and controllably. Cleanly is a complex word here, but basically it means that there should be a unique chemical pathway to form a compound. If there is a certain precursor that can do reaction A and B simultaneously, that may not be ideal, because then you do not have exact control on what you are forming. You would also prefer a precursor that in one step forms the compound you want to deposit and not go through multiple stages of chemical reactions, because again that creates uncontrollable situations. In general, we want precursors that have wide deposition window, as it called. So, a wide range of temperature and pressures where they can do the chemical reaction and deposit material, because that gives the unit process engineer the widest flexibility in coming up with a recipe for an application. They must be non-contaminating, sort of obvious. They must be stable byproducts. So, the way the CVD works is that chemicals are taken to the substrate, they react, they form the compound that you want to form, but they also do form some byproducts, and those byproducts must leave. So, those byproducts must also be volatile. So, if you have a chemical reaction that is, for example, forming a precipitate, then that is not a good CVD precursor, because then that precipitate has nowhere to go and it will just deposit on the substrate, stay on the substrate, and then contaminate the film that you are trying to grow. So, even the byproducts must be volatile. The byproducts must themselves be non-contaminating. If a certain chemical reaction is forming metal particles, that may not be a very good precursor, because those metal particles will then contaminate the semiconducting layer that you are growing. And they must be stable themselves, because again, you do not want secondary or tertiary reactions to start occurring, because that is an uncontrollable situation. Finally, the precursor must be readily available, hopefully consistent, which is that on day 1 the performance and the day 30 performance is roughly the same. They should be pure, they should be cheap, they should be non-toxic and non-pyrophoric, because those two things tend to increase cost and associated dangers. In general, very hard to satisfy everything. Like in life, ideal does not exist, we have to compromise. A lot of the precursors compromise on these last two: readily available, consistent, pure, cheap, and non-toxic and non-pyrophoric. A lot of the precursors are actually pyrophoric, a lot of the precursors are actually toxic, and a lot of precursors are very expensive. There is a wide variety of precursors available. I can honestly not list it on this slide or in this lecture. I will just point you to some websites. For example, here is a Sigma Aldrich website that I took a snapshot of, and you can see that they are advertising around 222 precursors. Given that the periodic table has around 90 useful elements, there are more than 2 or 3 precursors for every element that is there in the periodic table. So, that is enough for this lecture. In the next lecture, we get into more details of the CVD, the mechanism. So, see you next time.